Hey guys, in this video the brilliant Mr. B is going to be taking you through solving inequalities for your AS, your A-level maths. Now there are some quite tricky examples in here, but he works through them nice and slowly, and they're at 3 different levels, so you can jump into this video wherever you feel most comfortable, and you can stop whenever you start to feel uncomfortable. You can challenge yourself a little bit, pause the video and then work out the answer yourself, and then check that Mr. B works it out the same way. There are lots of different ways you can use this video, but if you feel there aren't enough examples here for you, if you want some practice questions to go with this, then they are all waiting for you over on my website.
You're going to start off by revising really basic inequalities, build up to more complicated ones, solving them using algebra, and then finally graphical inequalities. So with the most basic type, you have something that resembles an equation. So we have 4x minus 10 is less than or equal to 14. And so the trick here is just pretend that the inequality symbol is an equal symbol and solve it as you normally would if it was a normal equation. So we're going to add 10 to both sides and we're going to divide both sides by 4. And so that gives us x is equal to 6. But of course, that's not the final answer because we took out the inequality symbol. So the final answer, you write down the x, you write in the 6, but you use the same symbol. So it'll be a less than or equal to symbol. And you always use the same symbol unless you're multiplying or dividing by -1. Looking at another basic example, we have x divided by 3 plus 5 is greater than 13. So again, just pretend that's an equal sign. Take away 5 from both sides, which would be x over 3 is greater than 8. And then multiply both sides by 3, which would be x is greater than and x times 3, which is 24. Now, at this time, I didn't write down an equal sign. I just kept it as the same symbol because it's pretty easy just to imagine it's an equal sign and treat it as one, but just write in the same symbol all the way through. Moving on to a slightly more difficult example, we have 4x plus 9 is greater than or equal to x minus 6. The first job is to collect up the x terms. Let's take x away from both sides. Then we can take 9 away from both sides and then divide both sides by 3, giving us x is greater than or equal to -5. So again, everything just works in the same way as it would when you solve a normal equation. Looking at one more example like that, we have 10x plus 9 is less than or equal to 7x plus 18. So again, our first job is to collect up the x terms. Do that by getting rid of the smallest one. It's a positive 7x. So we're going to take 7x away from both sides. Then we need to collect up the number terms. So let's take 9 away from both sides and then divide both sides by 3 to get x on its own. X is less than or equal to 3. For our last example, we have 4 lots of 4x minus 5. That's less than or equal to -116. Now, you could expand the bracket out first, but there's an easier way with things like this. We can divide both sides by 4 to just get the bracket on its own. And you divide the right-hand side by 4 as well, you get -29. Then we can add 5 to both sides and then divide both sides by 4. So x is less than or equal to -6. So basic inequalities works the same way as solving equations. You shouldn't have too much problem. Now, inequalities get a little bit more complicated when you work with them on a graph, but just like with the kind of algebraic inequality we just looked at, they work the same way as solving equations. Graphical inequalities work the same way as plotting lines on a graph. It should all be things that you've done before. So let's plot our 2 lines. So the easiest one to plot is going to be the y is greater than 3x minus 6. So what you do is you pretend that y equals 3x minus 6. So we have a y-intercept, which is the -6. So we know that this is going to go through the coordinate 0, -6. Then we know from the gradient is a change in y over x. We've only got a 3. If you only have one number, just put it over 1 as a denominator, because 3 divided by 1 is the same number as 3. That means our change in y will be 3 and our change in x will be 1. And so we can draw on a pattern like this where each time we're moving up by 3 on the y-axis and across by 1 on the x-axis. Now, where this changes a bit is with plotting a line, you would then draw a straight line through this. However, with this, because it's a greater than, we're going to do a dotted line. So a little key for this, if you see greater than or less than, draw a dashed line. If greater than or equal to or less than equal to, then you draw a solid line. And the reason for that is because you're not allowed values directly on the line if it's greater than or less than. You're not allowed the actual value itself. Where it's less than or equal to, then you are allowed values on the line. So just tell the difference between the two alternatives. So I'm going to do a dashed line in between the coordinates. And now we need to plot our second line. So y is greater than negative 6x minus 6. So let's use our same methods. We know that the y-intercept will be at negative 6. That's the same as the previous one. And the gradient is negative 6x. So with negative 6x, the gradient's difference in y over x, we have negative 6. There's no denominator, so put it over 1. So our y coordinate's going to go down by 6, and then the x is going to go across by 1. So go down by 6 and across by 1 to get our next coordinate. And make sure you do it in the other direction as well, which will be the opposite, which will be going up by 6 and back by 1. And then just get to the end of the graph. You do half of that, so we can go up by 3 and then across by a half. And again, this is a greater than, so it's going to be a dashed line. So far, this is exactly the same as plotting lines on a graph. So what's the difference? Well, we have the dashed lines, as you can see. But what is the greater than or equal to? That would be the same as well, wouldn't it? What we have to do now is also do some shading. If we're saying that y is greater than negative 6x minus 6, then that means that y can take any value above that line. So just shade in everything above that line. So everything in blue, this is a potential place where we are greater than the line. We're greater than negative 6x minus 6. Now, we also want to be greater than the other line, the 3x minus 6. So we want anything above that line. And so we can shade in anything that's above the green line. Now, with the shading in two colours, you'll notice we've got a blue section that's only above the pink line. We've got a purple section that's only above the green line. We have a section where I've coloured in blue and purple. Now, that section is our answer, where it's above both lines. So I'm going to rub off the shading. That's only one type. And this is something you might need to do. You might need to do a little bit of the shading just to indicate where it is and visually see where both sections are shaded. But once you've done that, rub it out so you can't see it. And now we can shade in the area where both parts are shaded, the blue part and the purple part. What this means is any coordinate in the shaded area will satisfy both equations. So no matter what coordinate you choose inside that shaded area, then it's going to be above both of those lines. Y is going to be greater than negative 6x minus 6, and y is going to be greater than 3x minus. Where you can't choose coordinates, though, are coordinates that are directly on the line. That's what the dotted bit means. So let's look at another example. And again, just pretend that those less than or equal to signs are equal signs and proceed as you would when sketching lines on a graph. Let's do the positive line first. So y is less than or equal to 6x plus 2. So we have our y-intercept at 2, because the y-intercept is always where the x-coordinate is 0, and we get a number for y. It's always the number in the end. And then we can look at the gradient. So the gradient is a change in y over the change in x. If it's only one number, that takes the place of the y. So just pop a 1 in as the denominator, because 6 divided by 1 is the same number as 6. That means we're going to change by 6 on the y-axis, so going up by 6, and 1 on the x-axis, going across by 1. We can go down by 6 and minus 6, and then that'd be minus 1 as well. Once you've done that, because it's less than or equal to, and got equal to in it, we can do a solid line. So any coordinate on this line is going to satisfy the equation. Now let's have a look at the second line. So y is less than or equal to negative 5x plus 13. So we have our y-intercept plus 13. That'll be at 0, 13. And our gradient's negative 5. So the gradient's y over x. That'll be negative 5 over 1. And it's going to go down by 5 and across by 1. Each time, we're going to go down by 5 and across by 1. And again, this is a less than or equal to, and it's got an equal sign in it. Then you do a straight line with no dashes, a solid line. The last thing to do is to figure out the shading. Now, less than or equal to means one below the line. That means one below the green line. Just do a little bit of shading below just to indicate the places that will go. And we also want below the blue line. So go into that in a different colour. And what we want is the place that we've shaded in both colours. And we should be able to see that we've shaded this bottom triangle here in both colours. So this is the answer. Any coordinate in this shaded area, or actually on the line itself, is going to satisfy both equations. Then just rub out the shading you use for your working out further up. So now we have visually shown on a diagram our shaded area, the solution to the equations. Moving on to the next example, we're going to plot the line y equals 6x plus 9. So we have plus 9. That means we have the y-intercept at 0, 9. And we have the gradient, which is 6. If the gradient difference in y over x, that'll be 6 over 1. Our y movement is going to be 6, and our x movement 1, and also back in the other direction. Then this is a greater than or equal to, so we've got an equal to in there, so we want a solid line. Do the same thing with the second one. Y is less than negative 3x. No, there's no y coordinates. That means there's going to be, it's at 0, so 0, 0 will be the y-intercept. Then with the gradient, we have negative 3, so gradient being y over x, that'll be negative 3 over 1. So we'll go down by 3 on the y-axis and across by 1 on the x-axis, this kind of pattern. And then, of course, go back the other way. And then it's going to be a dashed line in between because it's only a less than. There's no equal sign in this. So we're not allowed values on the green line, but we are allowed values on the blue line. Final thing is that we just assume these are equal to, but actually they're inequalities, so we have to do some shading to show the inequalities. So if the blue line up to greater than or equal to, so we want anything above the blue line. And the green line, it's less than, so we want anything below the green line. And we'll find the area that's shaded in both colours, and that area is going to be the answer. And it's the area on the left-hand side. Now, you see, sometimes we've got a large area, the shading is quite a lot of work. You don't need to do a kind of consistent, nice, solid shade like this, where it's all completely shaded. You could do cross-hatching, so you could just do some lines, and I'll show you that on the next example. As long as it's clear which area you mean, then that's going to be fine. Fine, just rub out any extra shading you did as part of your working out. We don't want to see that on the final answer. Now, we can also do this with quadratics. You'll have to have a quadratic and a linear line. Let's do the linear one first, it'll be easier. So y is less than or equal to 3x minus 2. That means we're going through negative 2 on the y-axis, and we're going up by 3 each time. And then it's a less than or equal to, so it's going to be a bold line. It's going to be solid, it's not going to be dashed. The difficulty now is going to be the quadratic. Now, you could actually use substitution to plot this, but there's a few shortcuts we can use. So, for example, we can see that we have the negative 8 on the end. That is going to be a y-intercept. So we would find negative 8 on the y-axis. We know our quadratic's going to go through that point. We can also use the quadratic formula to solve the quadratic if it's equal to 0, which we'll find as the x-intercept. Because we've only got the y-intercept so far. So that would be negative b plus or minus the square root of b squared minus 4ac all over 2a. With us having a, b, and c being the coefficients on the x squared, the x, and the number on the end. So a is going to be 1 because we have one lot of x squared. So let's swap all the a's to 1. 2 times 1 is 2. With 4ac, that's going to be 4 times 1. And the coefficient for c is negative 8 times 1 and times the negative 8. b is 4, so let's swap the b's to 4s. And then we can start to work this out. So 4 squared is going to give us 16. And then the 4ac part, that's going to be 4 times 1 times negative 8, which is going to give us a negative 32. Be careful with negative numbers here, because this is going to give us a double negative. And so 16 plus 32, that's a double negative, will give us 48. So altogether, we have negative 4 plus or minus a square root of 48. So let's take the plus or minus to be a plus. That's negative 4 plus the square root of 48. And then divide the answer by 2. To one decimal place, we get the answer 1.5. So that means that one of our x-intercepts is going to be at 1.5. Then we can take our plus or minus to be minus, that's minus 4. Take away the square root of 48, and then divide that by 2. And to one decimal place, that gives us negative 5.5. So we know the other x-intercept. We can also differentiate it to find the gradient when it's 0, which will be the turning point of the curve. So if we have x squared plus 4x minus 8, it's y equals then dy by dx, differentiate it, bring the powers down, so it'll be 2x, and reduce the power by 1. So power 2 becomes power 1. Same thing with 4x, bring the power down. Well, if there's no power listed, it'll be a power 1. 1 times 4 is 4. And then bringing x to the power 1 down to x to the power 0. X to the power 0 just means multiply by 1. Then with the final one, within negative 8, there's no x listed at all. That means it'll be x to the power 0. When you multiply by 0, you get 0. So we lose that final term. Now you want to solve this when it's equal to 0, because when the gradient's equal to 0, that's a turning point of the curve. That gives us 2x is equal to negative 4. And so x is equal to negative 2. So the turning point of the curve is going to be at negative 2. Well, what about the y-coordinate? Substitute that in there. So we're going to have negative 2 squared plus 4 lots of negative 2 take away 8. And that's going to give us 4 plus 8 take away 8, which altogether is going to be, well, it's actually going to be 2 take away 8. So altogether, that'll be negative 12. So that'll give us the coordinate, -2, -12, for the x and y values of the turning point. Now, with those 4 points, you can make a fairly good sketch of the quadratic. If you want a bit more information, you could use a bit of substitution for a bit more of a guide. So, for example, we've got the turning point is at 1.5. So to get a good sketch, you might want to look at 2 or 3. I think I'll have a look at what x equals 3 looks like. 3 squared is 9, plus 4 lots of 3 is 12, and take away 8, that gives us 13. So when x is 3, we're going to be up at 13. And that's really all the information we need to sketch this, because it's also going to be symmetrical. So for example, look at the turning point, we can see that 2 to the right, we've got our next coordinate, 2 to the left is going to be at the same height. And then with the 3, 13 that we just found, that's also going to be on the other side as well. So that's 1.5 away from the previous coordinate. So we'll go to the last coordinate and go 1.5 back. That's also going to be at the height of 13. So we're using a real mix of things here. We've read off the y-intercept for the quadratic. It's -8. We've used a quadratic formula to find where it intercepts the x-axis. Then we've differentiated to find the turning point. We've used the symmetry of a quadratic to fill in a couple of the points. Then we use substitution to find another one. So lots and lots of different methods. If you're not comfortable with all these methods, then you can just use substitution to plot the quadratic, and we'll show that with the next example. So you'll be able to decide which one's best, but for now, let's plot this one. So I'm just going to sketch the curve. It's going to be a solid line that's less than or equal to, so you can have dashed lines on the quadratics as well. Come around to the turning point, and then continue your curve upwards. So now we need to do our shading. So we want below the green line that's less than or equal to. So we're on the shading in pink here. This is anything that's below the green line. Then it's also going to be below the blue line, because that's less than or equal as well. And you should be able to see the area. You can see both bits of shading. It's the area on the right hand side. So I'm going to rub out the shading that I don't need. And then what I'm going to do is I'm just going to rub out the shading that's correct as well. I'm going to show you now the method of how to shade in without having to actually shade in every single last bit, which with a pencil might take quite a long time. So to use a technique called cross-hatching, so literally do a set of lines, like so, make them parallel to each other, and then do it perpendicular to that as well. And again, make them parallel to each other. And so this clearly shows which section you want to shade, but you're doing it without having to actually shade in every single last bit and spend ages with your pencil. So for our last example like this, so we have y is less than or equal to 2x minus 12. So let's plot that first. It's going to go through -12. The gradient's 2, so it's going to go up by 2 each time. You can draw straight lines with only 3 coordinates, but the more you draw, the better it's going to get. If you draw a straight line with only 2 coordinates, then if you make a mistake, it's going to be difficult for you. Where if you have 3 coordinates, if you make a mistake, one of the coordinates shouldn't actually be on the line, so you know you've made a mistake. Now, with the quadratic, we'll do this one using substitution. I will start off with, though, the -6 means I know that at 0, this is going through -6. It's going to be a starting point for my substitutions, because now I know that the numbers around 0 are going to be ones to look at. So with that in mind, let's have a look at x is equal to 1, 2, and 3 first to see what we get. So if it's -x squared plus 7x minus 6, that'll be -1 squared plus 7 lots of 1 take away 6. So altogether, that'll give us -1 plus 7 take away 6, which is 0. So that gives us the coordinate 1, 0 to plot. Looking at 2, same thing. This time swap in all the x's for a 2. That's going to give us -4 plus 14 take away 6, which will give us 4. That'll be the coordinate 2, 4. Now let's have a look at 3 next. You might think this will take a while. You are right, it will take a while. It won't take as long as you think, though, because it's going to rapidly go off the page. But I think the previous method is faster. We have to be confident with more maths for the previous method. So now we have -9 plus 21, take away 6, which gives us 6. That's the coordinate 3, 6. So now let's have a look at x is equal to 4. Now my line looks a little bit odd at the moment. I think it should look a bit clearer with the next one, which would be -16 plus 28, take away 6. That gives us 6. That's the coordinate 4, 6. And now what we can see is that actually we've got the turning point of the curve here. Now, we don't need to do 5, 6, and 7 because this is going to be symmetrical. So we just need to match the heights for 5, 6, and 7, like so. Now, for the next one, we could do -1 and use the symmetry to get 8 as well. And that'll be lots of complicated negative numbers. I think it's probably useful to actually look at x is equal to 8, but you should get the same answer from -1 as well. -64 plus 7 times 8 which is 56, and then take away 6. And that gives us negative 14. That's a coordinate 8 and negative 14, which is going to be down here. So again, negative 1 will also be negative 14 as well, because it's going to be symmetrical. Now, it's a greater than or equal to, so we're drawing this with a straight line with no gaps. And so you need to make a decision now. Do you prefer doing it by substitution? Do you prefer doing it using a mix of skills? And it's up to you which one to use, really. It's just sometimes substitution. I've been quite lucky here, only need to do 5 substitutions. You could end up doing quite a lot more if you're unlucky. Now we need to look at shading. Now it's going to be less than or equal to the green line. So below the green line. So do a bit of shading just to indicate where that will be. But then it's going to be more than or equal to the blue line. So it's going to be above the blue line. And so we want the area that's shaded in both colours. And we can see the area that's shaded both pink and purple on the right-hand side. So we're going to shade that in. And again, if you do a solid shade like this, which is relatively easy for me on a computer, or you can do a crosshatch like I showed in the last example, which is a lot easier when you're using a pencil. Finally, rub out the shading using your working out, so your final answer is nice and clear. So any coordinate inside the purple area or on the line or in the edge of it will satisfy both equations. We can also use graphical inequalities to solve algebraic inequalities, and particularly ones which are quadratic in nature. So let's have a look at the one we've got. So we've got x squared plus 7x plus 10 is less than or equal to 0. But again, the trick is pretend it's an equal sign for now. If we were to solve this, well, we can factorise it first. And I think we can do it by inspection. If it's either 10, that would be 5 times 2. And for the 7, that would be 5 plus 2. So now it's factorised. We're going to make it be equal to 0. We can have the first bracket be equal to negative 5. Because negative 5 plus 5 is 0. So we're multiplying by 0, we get 0. Or the second bracket could be equal to negative 2 for the same reasons. So we have x is equal to negative 5 and x is equal to negative 2. Well, now you might think, well, let's just put the inequality symbol back in. We're going to have x is less than or equal to negative 5 and x is less than or equal to negative 2. Now think to yourself, does this make sense? Let's show it on a number line. 0, negative 1, negative 2, negative 3, negative 4, negative 5. Let's go down to negative 7. So we have a number line. Now, we say that x is less than or equal to negative 2. So we can show that like this. Solid circle for equal to, and it's pointing in the right direction. We'll also say that x is less than or equal to the negative 5. And it's going in the same direction as less than or equal to. Now, doesn't this make the less than or equal to negative 5 answer completely irrelevant because they're both less than or equal to? And if you have a look at the diagram, we'll figure out that this isn't actually what's happening. This is incorrect. So let's have a look at the diagram for this. So we know that the x-intercepts are going to be at negative 5 and negative 2. We know the y-intercept's going to be at 10, because it's a plus 10. And then we need to sketch the rest of the quadratic. Now, I'm not going to go through that again. I've gone through 2 examples using 2 different methods to sketch the quadratic, and we have the video on quadratics where these are sketched as well. Now, to sketch this, all it was, I used symmetry for the point I'm going through right now. And then for the turning point, I just did a quick differentiate for the turning point. I'm not actually that bothered about how accurate this is, because you'll see in a moment why. Because our answer is not going to be a diagram answer, it's going to be a written algebra answer. When we look at this, we're saying that it's got to be less than or equal to 0. So I've plotted y equals x squared plus 7x plus 10. And then for the other side, we're going to plot y is equal to 0. And so what we want here is, we want the part of the curve that's below that line. And we can see the part of the curve below that line is the part I'm highlighting in purple here. Now, what that means is, on our number line, that the bit that satisfies the equation is not less than negative 5 at all. If we just label negative 5 is going to be everything to this side, to the left-hand side. And label the other point negative 2, what we can see is we actually want the bit in between negative 5 and negative 2. That's the bit that satisfies the equation. So our number line actually should look different. Our number line should be in between negative 5 and 2, as you can see now in the diagram. And that's the correct diagram. So what does this mean for our final answers? So it's not going to be a less than or equal to negative 5. It's actually going to be a greater than or equal to negative 5. And so what you find is, when you solve a quadratic, one of the answers will have the same symbol as the question, but the other answer will have the opposite symbol. And you can see why visually here, because we're saying which part of the curve is less than or equal to 0. And we can see that only the minimum point of the curve is less than or equal to 0. And it's the part of the curve in between negative 5 and negative 2. So that's why the answer needs to be the way it is. Another thing is you don't need to plot the curve completely accurately, like I said, because you're just getting a rough idea of where the answer is going to be, but the curve itself is not the answer. The answer is showing that x is greater than or equal to negative, and x is less than or equal to -2. One extra thing you might see is you might see this as one inequality symbol. You might see it like this. So you might see that x is going to be less than or equal to -2, and -5 is going to be less than or equal to x. And that just means exactly the same thing as the thing above. And if you think about it, we're saying that x is okay in the center area. So x is in between -5 and -2. So just be aware of that answer as well, because you might see that on math schemes. You might even be asked to express your answer in that form. Next inequality is -x² minus 4x minus 3 is less than or equal to 0. So we can factorize this. We can take the negative out as a factor of everything first to make it easier for us. Then we can factorize the brackets. And we can do it by inspection. To get the 3, it's going to be 3 times 1. And to get the 4, it's going to be 1 plus 3. So in our final answer, to make this equal to 0, we need x to be equal to -1, because the -1 plus 1 is 0, and then we're multiplying through by 0 to get 0. And x will be equal to -3 for the same reason. As we know from the previous question, we've got to put the inequality symbols back in, or they're not going to be equal signs. So we need to think about what these symbols are going to be. And so now we need to plot this on the graph. Now, plotting the first half of this, the left-hand side, that's the curve we've been working with, quadratic. And we're also going to plot the right-hand side. The right-hand side is going to be y is equal to 0. And the right-hand side is going to be y is equal to -x² minus 4x minus 3. So we know the x-intercepts are at -1 and -3. We know the y-intercepts at -3 as well. Now, again, we could do substitution and draw the entire curve accurately. We could differentiate and find a turning point. There's various things we can do, but none of that actually matters. I'm just going to roughly sketch my curve through, because the actual answer on the diagram doesn't matter here. The diagram's a tool to help us solve the inequality algebraically. So that might be inaccurately sketched. What matters is the next bit, which is we want when the curve is less than or equal to 0. So where does the curve go below 0? It goes below the x-axis. Well, you can see there's a section on the left-hand side that goes below. There's also a section on the right-hand side that goes below. So we have two sections this time. This is different to the previous question. Now let's have a look at the figures here. So we have -3 and -1. So we have the section before -3 is below. So that will be less than or equal to -3. So, for example, -4 is in that section, -5 is in that section. Also, everything above -1 is in that section. X is greater than -1. And so now those are two answers. X can be on either side. It could be on the right-hand side and be greater than -1, or it can be on the left-hand side and be less than -3. What you're not allowed, though, is you're not allowed answers in between. So -2 doesn't satisfy this equation because it's not greater than or equal to -1, and it's not less than or equal to -3. And in fact, in this case, -2 is the only whole number that doesn't satisfy the equation. But of course, you can have decimals in between as well that will. Unlike the previous question as well, we can't rewrite our two answers to be one simple expression, because we have x on the left-hand side and on the right-hand side, and they don't cross. So there's no way to write it as one expression. So now looking at the next example, the first thing to do is solve it algebraically as far as you can go. And again, these are fairly easy quadratics that you can solve by inspection, although you could get ones where you have to use a quadratic formula or completing the square. So for this one, to get 4, that'd be 1 times 4, and to get -5, we'd be taking away 1 and taking away 4. Which means that x would be equal to 2, or x would be equal to 4 if this was solving a quadratic equal to 4. However, it's not equal to 0, it's less than or equal. So we need to figure out the symbols as usual. And the way to do that is to sketch the lines. Sketch the right-hand side, which is the 0. So you sketch y equals 0. And these questions are all equal to 0, but you can have it equal to other numbers. And then on the left-hand side, we're going to sketch the quadratic. So we know what the y-intercept is, and we know where the x-intercepts are at 1 and 4. And from this, we can sketch the quadratic good enough to figure out which way around the greater than or less than's are. So it's going to look like this. I don't know how far down it goes, but it's not going to make a difference. I don't know how rapidly it goes off the page, but again, that's not going to make a difference, because the only bit we need to know really is where it dips below the x-axis. Now, this has to be less than or equal to 0. So you look at where the curve is less than 0, and it's less than 0 in between. And what's it in between? We're in between 1 and 4. That means that x is going to be in between 1 and 4, meaning that it's greater than 1 and it's less than the 4. And since x is in between, you can write it as a single expression. 1 is less than x, and x is less than 4. With everything being less than or equal to, because that's what we have in our original question. Let's have a look at another example. So x squared plus 6x plus 8 is greater than 0. So we can solve this to a certain extent. We can say that to get 8, it's going to be 4 times 2. And to get 6, it's going to be adding 4 and adding 2. Which means that if it was equal to 0, we'd have x is equal to negative 4 and x is equal to negative 2. But it's not equal to 0, so now we have to draw the diagram and get an idea of which symbols we're going to be using. So again, we're going to plot the right-hand side, which in this case is 0, and we're going to plot the right-hand side, which is x squared plus 6x plus 8. We already know enough about the quadratic to solve the question, so we know that it's going to go through 8 on the y-axis, and we know it's going to go through negative 2 and negative 4 on the x-axis. We can give it a sketch, and then have a look at what we're saying. So we're saying it's going to be greater than 0. So where is this line greater than 0? It's greater than the green line on the left-hand side and on the right-hand side. So we have two separate answers. Pop the numbers on the diagram to help you. You've got negative 4 and negative 2. So x can be less than negative 4 and x can be greater than negative 2. And for this one, there's two separate sections where x can be, so we have two separate answers. Moving on to our final example, we have negative x squared plus 6x is less than or equal to 0. When we factorise this, we don't have a number term at the end, so we're not going to be able to do double brackets, so we can take an x out for single brackets. So that will give us x and then negative x plus 6 inside the brackets. Now, we don't really want a negative inside the bracket. It's going to make it a bit more complicated. So a better way of doing this, actually, is to get rid of the negative sign first. So take out the negative as a factor. It's going to flip all the signs. And then factorise. Take x out. And now something makes a bit more sense. So we're going to have x is going to be equal to 0. And x is going to be equal to 6 to make the bracket equal to 0, or to make the outside equal to 0. So we still have two answers, even though we don't have double brackets. We don't know what the symbols are going to be, so we're going to have to sketch this. So again, draw the line y equals 0. Sketch the quadratic, and all we need to know is the intercept, which must be 0. Then we have the x-intercept, which is at 0 and at 6. The difficult bit here is that the y-intercept can be unclear which way around it is. So you kind of need to know that a negative quadratic is going to be a kind of N shape, with the positive quadratics are U shapes. I don't know how high up it's going to go, but this is enough to solve the question. When this graph is less than or equal to 0, and so that's when it's below the green line. And we can see two separate answers on the left and the right sides. Take a look at the numbers. We have 0 and 6. So x is going to have to be less than 0 or greater than 6. And it's less than or equal to, so put the equal sign in there as well. X can be in two different locations, so we have two different answers. If you're asked to list some values that satisfy the equation, you should use any negative number, negative 1, negative 2, negative 3, and so on. And you can use any positive number, 6 or above, 6, 7, 8, 9, 10. Numbers that don't satisfy this are the ones that are in between 0 and 6. So 1, 2, 3, 4, and 5 do not satisfy.